Hi, everyone. Welcome to the Dynamic World session, hands-on practical training session at Geo for Good. Tanya Birch, Google Earth Outreach.
Tyler Erickson, Developer Relations for Earth Engine and other products.
And then we also have TAs, some folks who worked on the production of Dynamic World, and some folks from our communities. We have Ollie Gainen in the back, Ujjwal Gandhi, Elise Mazur, thank you. And I'm not sure whether I saw Valerie. Oh, there's Valerie in the back of the room. Am I missing anyone? Is Chris joining us? Well, anyway, we'll see. Okay, Chris Brown? We'll see. He might be joining us later. We have a Q&A session at the end where you can ask questions, technical questions of the developers if you have any. So our agenda today is we're going to spend a little bit of time, setting the stage, introducing Dynamic World, giving you a little more, some apps to explore Dynamic World. That's going to be quite brief though, because we're going to go right into our hands-on session of getting to know the Dynamic World dataset. This is exploring the structure of Dynamic World, and Tyler has put together some really awesome scripts to help us. And these are also based upon Ujjwal Gandhi's from Spatial Thoughts tutorials, which are available online. So if you can watch this recording afterwards. It'll be posted online. But it's also going to be, Ujjwal has amazing content to access online. And then in the second portion of the workshop at 11:30, also in this room in Discovery A, we're going to get really hands-on with building derivative data products, which, if you heard the plenary, it was really about, this is what Dynamic World is about, right? It's not a static map. You build derivatives with, the class labels or the probabilities, and then produce something more custom with local knowledge. So just to reiterate, you just heard me say this, so I'm not going to spend too much time repeating what Dynamic World is, but it's a 10-meter land use land cover data set. Global coverage. It parallels the S2 L1C collection. So we take any scenes that are less than 35% cloudy and run those through an AI model. I'm grossly simplifying the process. And then produce a parallel image collection with the same collection IDs to make it easy. Everything that went into the production of Dynamic World is freely open and accessible. That covers the National Geographic Society training data set of over 24,000 hand-labeled pixel Sentinel-2 scenes, polygons. That's available on Pangea, which is an open data repo. The test data, the validation data is also open. Easiest way to find those is look up the scientific data descriptor publication, and I think it's still on the cover, so that should be easy to find, the Dynamic World paper. So the easiest way to access Dynamic World is, voila, through the Earth Engine data catalog. So we created a new section underneath Sentinel-2 underneath Sentinel for derived data sets. So there's Dynamic World, there's ESA World Cover, there's a number of other Sentinel derived data sets in there. And then we're gonna, Tyler will walk you through like how to actually access it in the code editor in a minute. But I also want to call out Valerie's amazing Dynamic World app that allows you to pick any pixel on Dynamic World, set a date range. So you can choose your start date and your end date, and then it does a mode composite. And then if you click on a point on the map, you get a chart like this. And the chart shows you the variability across probabilities. And if you click on a specific vertex in the chart, it loads the single scene prediction as well as the Sentinel-2 image that it was predicted upon. So it's a bit of an Easter egg. I want to call it out because it's a little, you have to find it. Like you have to click on the pixel. But I find it to be an incredibly valuable way to explore Dynamic World and explore the depth of this data set, whether you're a coder or not. And just a call out to Ujjwal, who produced 3 tutorials for dynamic world, which, you know, we're going to walk through today, so I'm not going to spend too much time talking about it, but he's here in the room if you have, you know, I don't know, questions about the tutorials themselves, or requests for, you know, additional tutorials that you wish you had. So with that, I'm gonna turn it over to Tyler.
Thank you, Tanya. I have the mic here, so I'm good. So if you go through the Geo for Good agenda, there is a way to get to this session and the whole slide deck. But I want to point you to a shortcut if you haven't opened the presentation right now, that you can just go to this short URL there to get a link to the code that we're going to be working with today. So I'll leave that up for a few minutes. And I am going to have quite a bit of code up here on the screen that I'm asking you to follow along. So if you are in the back and have any concerns about being able to read small bits of code, please move up. I guess we'll see when we get to it, but it's often hard, even on a large screen like this, to see some of the details of the code when we're doing a hands-on session like this. All right, anybody need more time? This URL right here? Okay, we got a few people that are still bringing that up. All good? It is a bit slow to load depending on how many repositories that you already have in the code editor, because it's actually going to be bringing those up. I'm going to click on it now, and we'll see how slow this one is as well. Mine came up pretty fast because I had just created a test account for this week, so I don't actually have that many repositories in here. But what that link should have taken you to is a script repository, G4G22-dynamic world, and there will be a series of scripts that are within there. And I'm going to assume that most people are familiar with the code editor. And if you're not, please raise your hand if you need any of the direction or any other questions you have from the TAs. But briefly, it's a collection of code. It's read-only for you, so don't worry about like changing it or overwriting anything. But you can click on a script on the side in the repository, like I clicked on the first one, and it will load it up here. And don't worry about experimenting. That's what we're here for. I mean, you can basically delete large parts of it, and it will not run anymore, but that's fine, because whenever you get stuck and you get an error, you can always go back, or if we've moved on to the next section, you can click on one of these links on the side, because it's going to be pretty much a progression. We have a progression of all the ones that start with 1 all the way up to 1G, and then we're going to switch over to some slightly different scripts at the end. So I do encourage you to experiment as we go along, just to see, because I'm trying to teach this basically of that we'll have some starter scripts that will allow you to see results without having to type in every little detail, but they're simple enough that you can tweak and change, whether it's the location, the bands, etc. We're going to do a lot of exploration, I guess, of the data set here. So do experiment. All right, so I'm going to start with this first script here. Let me resize my screen so I can get it almost all on there. I'll start with this much. And I'm just going to start explaining this in fair detail, and then the other scripts are just going to build upon this. So I've broken it into a little bit of sections that will kind of give us some constants at the top, and then a section of code. This one's going to deal with displaying Sentinel-2 data, which Dynamic World is based upon in this script. So we're going to start off at the top. It's just defining, like, where do you want to start in time? In this case, it's January 1st, 2019, and we're going to look at a time interval of half of a year. Feel free to change that, once again, if there's a particular time that you're interested in. Maybe it's not the winter season in North America, but you want something else. And then, based on those constants, we'll calculate an end date that we can use for filtering the collections, both Dynamic World and the underlying Sentinel-2. This script here is going to give us some visualization parameters for Sentinel-2 that are defined here. We will then load up Sentinel-2, and it's Sentinel-2 harmonized. One of the interesting things about this data set is that it was being produced for a long period of time with certain scaling parameters, and then in January of this year, they changed. And so there's sort of like a step function in the processing. And they haven't gone back to reproduce, ESA hasn't gone back to reproduce all of the other scenes so far. So we created one in Earth Engine that is considered to be harmonized in the sense of these scaling parameters, so that when you load that up, you don't have to worry about how they changed over time. We have done that adjustment for you. If you don't use the harmonized version and you're looking at time series analysis, you might actually see step function in your result. So just want to point that out there. So we're going to use the Sentinel-2 harmonized data set, filter it for our start and end date, and then just for the purposes of getting started, we're going to pick out a single scene to work with. And in order to make it a scene that doesn't have too many clouds, we'll filter it down to a particular location and then filter by the cloudy pixel percentage to be less than 20. So less than 20. And then once we have filtered to that, we're going to take the first image in that set. So it's the most recent scene without that many clouds. It still might be some clouds in there, but it should be less than 20 overall. And then we'll basically display that on the screen and extract out the ID of that image that we pulled out here so we can use it later on to match up with dynamic world. So let's run that. And the geometry that I put in there is right around basically the campus where we are right now in Mountain View. Feel free to change this to anywhere you want around the world in order to get imagery that's relevant to you. And then with the print statement that we had up here at the end for that ID, it's going to print out the unique identifier for that Sentinel-2 team, or Sentinel-2 scene. The good thing is that the Sentinel-2 collection and the dynamic world collection, they use the same IDs at the end. They have a different prefix, but at the end they use the exact same ID. So it's useful to join them together. So I will pause there just to make sure that everybody is caught up. Raise your hand if you need any help from any of the TAs. I see at least one hand there. And another one there. Okay. All right, so we got the hands raised covered, so I'm going to move on to the second script here. And this one is going to start, once again, with the same code. What I have on the screen there is pretty much identical code from the last script that I had. But now there's a new section down here that is code related to the dynamic world dataset. So we'll start off by referencing the image collection of dynamic world. I don't remember how many Sentinel-2 scenes are in there, but it's hundreds of thousands of scenes. It's a large collection. We're going to basically put down some information into a JSON structure, a JavaScript structure, on the class information for the probability bands of dynamic world with a color that we might want to use for visualization so that trees look green, et cetera. Kind of the standard colors that you've seen so far for dynamic world. And then there's a little programmatic code that you don't have to really worry too much about how it works to extract like the colors and the classes out of that list before. I just like to do this because I find it easier when I'm actually writing a script like that to put all of the information together rather than having separate lists. But this code below breaks it out into separate lists. And the lists here will be like a list of probability bands and the palette that is used. So the palette is used for the visualization later on. The probability bands is used when we're doing classifications and other work with it. And then finally, we're going to take that entire dynamic world image collection and apply a filter where we're going to match the image ID that we found before when we were basically filtering for the geometry. And then as a last step, add that to the map so that we have both, should have two layers at this point. And you can toggle between them if you want. I guess Sentinel-2 is turned off by default. But this is the underlying Sentinel-2 image. And then this is the dynamic world. And what I'm using right here is labeling on, or using the bands that I'm displaying here is the label band. And we do include that label band in dynamic world imagery, but this is the only time I personally use it, is when I'm displaying a single image. It's convenient. Whenever you're trying to aggregate over a large collection of images and combine it down together, then it gets a little bit confusing what to use for that label classification, because it's categorical. It's basically throwing away a lot of the probability information and just summarizing, hey, what's the dominant class for that particular scene? So I think this is the only time you will see in this code when I'm actually using that label directly from the dynamic world. All right, but at this point, we have both a image and dynamic world image. Any people need some help from the TAs at this point? So it looks like we resolved what went on with the first script. Excellent. All right, so I'm going to jump to the next one. And this is basically moving away from doing operating on an individual image to using more of the power of Earth Engine to work on an entire collection of images at once. So let me give myself a little bit more real estate to go through the code here. This will be the same. And then, well, this will be the same until about right here, where we start, instead of looking for a particular single image, we're filtering by the start date, end date, and then we're going to select the probability bands and reduce them all. So that will mean that, you know, the probability of water across all of the images in that collection for the time interval that you filtered will be reduced into a single value, the mean of that series, or the mean of that probability. And then finally, I have one line here that adds a little bit of methods chaining to get what I want, the result I want, but I'll explain it here, is that we'll take the mean probability, which contains each of the 9 dynamic world bands and the mean probability of the entire stack of images, convert that to an array, look through the array for the argument that's the maximum of those bands, and then get it out, and then rename it. And what do we rename it as? Looks like it's a mystery here because it's off the screen. Label. So I'm sort of calculating what that label field was on the single image, but in this case, it's after we have aggregated all the probabilities first, and for the one that is the top probability of all the different dynamic world classes. So we could have done this on the single image, and we would have got the exact same data, or the same value that was in the label band. But I'm just wanting to demonstrate that and call that off, because I think that is, you know, chaining together these 3 would be kind of hard to do if you were looking through the Earth Engine docs, like trying to find out how do you manipulate an array or create an array-valued image and then look for something within the array, extract it back out. But this is pretty key for dynamic world. And then finally, we're going to take and display the Sentinel-2 data set. This time we're working with a collection. And in order to make it not so cloudy, I'm going to just take the minimum value just as kind of a reference. And then down here, we have this dynamic world class composite, which once again is the highest probability from this manipulation we did with the array of images, array valued image. So run that. And it's going to look somewhat similar, but the difference here is that we actually can do it over a much larger area depending on how I did the filtering. You know, it's not just a single Sentinel scene or dynamic world scene. It'll be wherever I go. And that's kind of the power of like operating on image collections as opposed to individual images. So any questions on that type of temporal aggregation? The key part is this line right here of how do you create a label, categorical variable from that list of probabilities of the classes. I see somebody waving or actually has a question there. All right. All right, looks like it's being answered by the TA, so I'm going to go on yet again. All right, that was kind of a neat visualization showing the classes, but as you heard in the plenary, there's a lot of detail that is lost when you just summarize it down to a categorical variable. And one of the ways to bring out more of the richness of the data is to do some adjustments to the colorization of that categorical variable. So this script here, which it has quite a few steps, so I will probably go through those rather quickly. It basically colorizes a hillshade operator to bring out the depth. You can actually see, where it looks dark or it looks like it's kind of lower down with this three-dimensional hillshade perspective. That's where it's lower probability, and where it looks like it's a plateau, that's when then the probability is relatively high. And the way that we do this is that we first figure out, what is the image with the highest probability value at each pixel, and that's not categorical anymore. It's taking the top probability value in this top one probability, and then converting it to an integer, passing it through a Earth Engine terrain function called hillshade, which creates a black and white kind of shaded hillshade, and then finally colorizing the image with these two lines by taking a visualization or converting the class composite into an RGB image and then multiplying it by that hillshade. So if I go back up here a bit to look at the results, this is your classified image. If I zoom in more to our area, actually I guess we're down here a little bit, it becomes much richer when you're looking at these transitions between the water and the shore, where you're going to have mixed pixels because it's shallow, or that it actually is sticking out of the water, right? And the pixel is composed of both water and land. But anyway, you can see a lot more variations in here. And that was how that, one of the examples in the plenary showed that how you could see like the Golden Gate Bridge doing a visualization like this. Let me see if there's anything else here that I got to cover. Nope, that's it for this script here, the dynamic world hillshade. So any questions at this point on what we're doing? Okay, I got a few. If you could either step to the mic, or the TAs have a mic that they can bring around, so either way, so we can record this.
Yeah. So just maybe an upper level thing, just to get me fixed. You're comparing now from January 2019 across all the years after that?
No, at this point, we are selecting an interval that starts January 1st, 2019, and it goes half of a year from there. That's what these two lines define.
So it's 6 months period?
Yes, 6 months. So the start date of January 1st would be here, and we are going to advance 0.5 years. So right now, we're not comparing. We are kind of cutting out a period of time that is 6 months in length.
Okay.
And that's our list of there will be several images, numerous images that Sentinel-2 took, and hopefully will pass the cloud filter test that we had put in there earlier. There will be multiple probabilities bands in each of those. We have taken the mean across each of those. So we have compressed this down to be a single image that once again has 9 probability bands, but they are an aggregate of a long time interval.
So how does that link to the seasonal changes in the area in there? So if we're talking about an area like in Africa.
So at this point, it doesn't. It's saying, because I did it for a half a year, I could have done it for like the growth period of a local growth time. Maybe it would be around here, April through June, and compared that to something in the fall. We haven't got that far yet. We're actually going to do something similar with the classes later on. But at this point, we're just taking a single interval, which I chose to be 6 months, but that might not be appropriate for really any type of analysis, as a demonstration. Yep. Any other questions at this point? Okay, I'll bring in the mic quick.
Okay. Hi, how are you?
Hi.
So if you zoom a lot to the pixel level and compare the classified image and the probability hillshade, there's like a slight, how do you say, difference between the two, like they're not matching. Is that by design or?
Is that a visual, a
Yeah.
spatial shift?
Aha, yeah.
Okay, that could have something to do with how the hillshade is calculated, that it
Oh,
might look
okay.
like it shifted just a little bit.
Okay,
But let's actually see what,
it's less than a pixel, but I was just wondering if
Yeah.
that was by design or like.
wait till it loads up here. And then
Gotta
flickering
like
on,
really zoom in so you can compare. I don't know if you.
yeah, at this point, I mean, it looked good along the edge that I was looking at right there. But
Like,
there's a few things that
if
could
you-
be going on. It could be the hillshade operator, because I'm seeing at some point it looks like it's a little shaded out there, and sometimes it looks like the darkness is inside. The other thing that goes on is that when you are aggregating over a series of images, it sort of loses the projection, and some of the operations that you want to do, you have to reassign a projection to the output. Because the original images all might have had different projections to start off with. In the case of Sentinel-2, they won't for a local area like this. But Earth Engine basically will say, I don't know what the projection is because it could be anything based on a collection of images that were used as input. So those are the two things that might be factoring into what you're seeing. But
Okay.
we'd have to look, I think.
And these are not created on the fly, right? Just like they're already processed, so. Just wondering, like.
dynamic world images, the Sentinel-2 images, the raw ones are already calculated.
Okay.
But all of this stuff that we're putting in the code where it is doing filtering or anything like that, it's being done on the fly.
Okay. Right. Thank you.
Sure.
So I would just want to mention what Tyler mentioned, that in the tutorials, there's a code that says set default projection, which assigns the default projection that you lose when you create this composite. So if you look at the tutorial, there is a call to set the projection before you do this. So that might help with this one.
Yep. And that will come into one of our later scripts when we do, I believe, when we do the classification. We do have to set the default. Oh, wait, no, it's actually in this one at this level. Yeah, this is what Ujwal was pointing out, is that there is an explicit assignment of the default projection because this mean probability is an aggregated image. And so we don't know what the projection is until you actually assign one to it, assign the default. So at this point, another thing that we could do, because we have quite a few layers right now, so it'll start getting a little bit interesting, is to play around a little bit with the inspector tool of Earth Engine to give us a little, I clicked right now on a point out in the water, somewhere out here. And it just gives you a summary of the values for all of the different layers of what you clicked on. The Sentinel-2 one is kind of interesting because you have all of these bands here by default are displayed. If you want to see individual values for the different Sentinel-2 bands. And then as we go down into the other things that are being displayed there, the classified image has a label. I clicked on water right now, so the label was 0. I believe that is the first class of dynamic world. But if I clicked on, for example, a red urban area, now it's going to say label equals 6. Just a quick way to explore that. And then there was that step where we converted into an RGB image to create the hillshade. So that's why we have a visible red, visible blue, green, visible blue, and then those were multiplied by the hillshade to adjust accordingly.
Hey, Tyler.
But this tool over here, the inspector, is really interesting to work with, especially when you're trying to understand a really deep multi-band image like dynamic world. I guess this was not the best way to describe that or to show that because we've already condensed it down to a label at this point, but on the earlier scripts.
Hey, Tyler.
Yep.
So that top one probability image.
Yep.
So that is, so you have a mean where you've got the mean value for the entire image collection for each of the classes, right? And now that you're creating the max, what is that representing? Is that the max probability?
Yeah, so
Yeah, if you had that.
let me go one step before there, and I will, actually I'll just add it as a map layer. And this is what I often do when I'm trying to explore, how an algorithm is behaving. I will basically just add a new layer, and then by default, I actually would turn it off because I don't actually want to see it on the screen necessarily. But then it will give me a little bit more information when I'm clicking over on the side here. And what I just added up there is the mean probability layer. So I now have, bring this out here a little bit farther. We have for each of the dynamic world classes the mean value across all the images in that time interval at the point that I clicked. And so you can see a variation in here. If I look for the one that seems to be the highest, it's water, which makes sense. I clicked out in the bay there at 0.66. And that next line there that extracts the maximum value, that's at a point going across all the bands looking for the highest one. Was that the question?
Yes. Okay.
Yep.
Yep.
Okay. Any other questions at this point on what we're seeing? All right. So right now we have, basically this script was showing a more intuitive visualization, but it's not one that we would normally use for further analysis, just for, as I said, visual interpretation. All right, the next script I have here, 1E, if you click on that, adds a little bit of code to aggregate information over a region. So there is a geometry that was defined here, just using the code editor. If you want to edit this, move it around, delete it, draw somewhere else, it's fine, as long as this layer always is called geometry, which is the default, so it's kind of easy to do that. But if you're interested in a different area, just click and modify what this polygon looks like or this rectangle looks like, and if you want, pick another tool. Let me move it a little bit back to that area, exit. And we're going to run this script, and then I'll step through what it's doing. So we're going to look at the spatial aggregation section towards the bottom. That's what's new in this one. And it's going to take that class composite that we calculated earlier by looking at the class that had the top probability, and then produce a frequency, or reduce using a frequency histogram. So there's potentially a lot of different categorical values within that region, especially if I drew the bounding box over a large enough area. And we can basically calculate pixel counts for each of the classes using this reducer frequency histogram. I've put a few extra parameters in there, kind of the maximum that I want it to go in terms of aggregating pixels before it starts simplifying the scale. And this allows me to make the box really large, and it won't basically try to calculate every single image or pixel inside of there. It's going to pick the appropriate scale so that I'm not going to exceed this maximum amount of pixels, which is still quite a few pixels, basically, to try to aggregate, to come up with the estimate there. I guess the other code that is in there is to take those pixel counts that we calculated with the reduced region, and then down here we're just going to do some renaming to make them, instead of 0, we're going to see water instead, to make it a little bit more interpretable. And that is later printed out to the side so that if you're just looking at pixel counts, you can compare them in terms of the number of the pixels. This is okay approach if you're looking at a small region where the variation in pixel area is not going to change dramatically. But if you're doing this over large regions or going up near the poles, you would want to first do an extra step of converting it to an area, which there's some examples in the Earth Engine documentation about how to convert from pixels to area. But over a small region, this is going to give you a pretty good comparison of the different classes in that area. But it's hard to actually compare, just total amounts. So there's another step down here that's going to convert it into a fraction. So all of these should add up to 1. And I guess looking visually, there's a lot of forest in there. There's a lot of urban area in this this area of the box that I highlighted there. So if we looked in the built environment is up at around 0.36, and then wherever my forests are within there, trees, sorry, 0.52 in that area. So that makes sense for the region that I was highlighting. And there's no real change to the visualization map display at the bottom there. So any questions on that? It's sort of similar to any other data set in Earth Engine that you would reduce. Kind of the kicker for this is because it's a categorical data set, we can use that the reducer that actually calculates a histogram, frequency histogram. All right. Any questions before we go on? All right. We got 2 more scripts, so we're doing pretty well on time for this first section. And now we are finally getting to the point where we're going to do charting for a particular region. The region I shrunk down a little bit, and just for practice, we're going to start doing it over the water just to make sure that we can understand the behavior, and then we can move that region to some place that is a little bit more complex. But if we scroll down to the section that is charting class probabilities over time, that's the part that's relevant for here. And this first block of code up here is defining a function that's going to take a label and a color and produce a string that our charting library understands. So it looks a little bit obtuse up there, I guess, if you're just looking at what the function is, but that is the purpose of it. And that allows us in the call that is creating the chart to define a series for displaying on the chart that says the dynamic world class name and then the color. So that's all that, it's kind of a helper function up there. And the chart or the charting call that we're using is going to take a image collection. It's because we're using UI chart image series, which works on image collections, a series of images. And we're going to pass in the dynamic world time series that we previously calculated, reduce for the region that we have drawn on the map, doing it at a scale of 10, which is the native resolution of dynamic world, and then a little bit more with just configuring how that chart is going to look. And this is similar in some ways to what you saw in like the plenary of basically selecting a class. It varies over time, but you have one dominant probability here of water. It's not saying it's 100% certain it's water, but that's the closest match that it has. I'm going to take just a second and move it to different region here. Actually going to go see if I can go to the Golden Gate area. So this, once again, is an area that if we turn off the hill shade, you don't actually see the bridge. But there is some probability information there, variation in the probability that indicates that something's going on differently there. And we can run this chart at the same point. It's still, since it's aggregating over the entire region, it's mostly going to show us water too, so I guess maybe this is not the most illustrating example right there. Yeah, it's pretty much water. It wouldn't be until I got like down, let's try this as an experiment. You can use all kinds of different geometries for what you're reducing over. So I'm going to delete this one, zoom in a little farther, and then my geometry I'm going to take as a line. And we'll see how this works along that bridge, which probably will not be fully water as the dominant class. Run that again. Normally you wouldn't do this following a bridge, but if you were doing a transect across to something else. So it's lower probability at this point, but I can't really see what the other secondary dominant class was in there. All right, any question on that script? Questions are welcome, or anything else you saw up to this point. We're really doing pretty good on time. There is a question towards the back there.
Tyler, when you were out in the water, it looked like the maximum probability was 75%-ish. The dynamic world, they always add up to 100% in every pixel,
Yep.
right? Any insight about what it's getting confused by being out in the middle of the bay? I mean, that's water, 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 right?
It is water, water, water. I guess it depends a lot on what the sea conditions are, if they're, because water looks differently, I guess, under different wind conditions, where the sun is, whether there's anything dissolved in there. Also, just the atmospheric conditions are going to make it look not perfectly water. Remember that dynamic world is based on the top of atmosphere, Sentinel-2 values. So there are always going to be some atmospheric contamination there. So there are a few possibilities in there. Looks like Ollie might have some other input on that.
Yeah, we were just looking at that same thing, and it's also possible you could be seeing some tidal action there. It was close enough to shore, and the bay is only about 5 feet deep there. So you saw flooded veg was the class that came up when water came down. So possibly some tidal action, you're just sort of seeing through the water to the mud and maybe some vegetation there. Could be a paper in that.
Yeah, I'm just thinking of this dynamic world. How many PhD students' work could this power? You know, just basically trying to explore all of the variations around the world that is being enabled by this dynamic world. I'm actually looking a little bit farther out in the water too. I think this is a pretty good example of that atmospheric kind of changes. This is towards the edge of where the Sentinel scene would be. And so you're going to see things that don't look perfectly water right as you get towards the edge of a scene. So I think that's what those vertical lines are there. I'm not actually sure what these very distinct depressions, it looks like, in the water probability are over the bay. That's kind of another interesting artifact. Any other questions at this point? Oh, yep.
You also sometimes get ones like in the other direction, maybe because there's like geo-referencing or adjusting the projection.
So the question was, do we also get artifacts in the other direction due to the georeferencing? I guess I would expect that we might see them because of the way Sentinel-2 and Landsat and other scenes are. They usually have overlap as you go just because of the distribution. The satellite collects over the entire region, but it'll be broken up like that. I am not familiar, but maybe somebody who has been spending more time looking at dynamic world would know if there's any of those path row overlap artifacts that are apparent in there. Is that something, Ollie, that's come up, or no? Okay. So not that we know of, but there are other reasons for artifacts as well. Yep.
I have another question regarding the water and the weird artifacts that you were just seeing there in the water. I am curious if I know there's just the 9 classifications, but what about like within water, like for instance, seagrass detecting or anything like that? Is that a thing? I mean, would it notice that there's a change in the water?
If there is if that is expressed in the reflectance that you can see at the surface of the water, then yes, it has a possibility. I guess I don't know enough about what is going on in those exact areas to think of how shallow they are, whether the light is going to penetrate all the way to the bottom. Normally it's a pretty turbid area out there, so there's not a really large depth of penetration. Yeah. Yeah, I guess one thing I would think is like along the edge there, it's probably going to be a mix of water and something like bare earth, right when you get to there. Yeah, because that is the Sentinel image, you're seeing some type of color within there? Murkiness. But yeah, I guess to start exploring that, you could actually drop, and I'm going to delete this geometry that I'd been creating before. Sorry. I'll delete that one, start over. If I dropped a point kind of right at that interface, I would think there would be some more of a blending of classes. Let's make that large. Well, it's definitely got significant number of classes that are above, at least the 0.1 or 0.2% probability in there. So there is a mixture of potential results that are not necessarily stable there over time. Which would make sense if the water conditions are changing, whether becoming more or less turbid over time. Be fun to look at a place that has algal blooms or growth. Yes, they could if you're able to do visual interpretation to actually say whether it's something different than the main classes that we have. And this is kind of leading into what we're going to talk about in the second session. But it's also really good to have in situ measurements of like water quality or something that changes rather dramatically in time. You could correlate to very specific times of the satellite overpass. And if you do have that type of information, you might be able to use that to make a more detailed classification. Yep. All right, I think we'll jump to our last script then before the break. And this is G. This is our change detection that we are going to base it on the probability change from a time interval 1 that we define to a time interval 2 that we define. So going through the code here, I've modified my definitions of the time intervals to no longer, it's not start date anymore. We have start date 1 and start date 2 because we're going to have 2 different time intervals. First one starting in 2019 in January, second one is in 2021, so 2 years later. But for each of those, we're still doing that half a year, 6-month time interval. And then, so that's calculating the end dates for each of those time intervals, and then we use that later on in our script here. Just for visualization purposes, we use those 2 different start date, end date pairs to filter Sentinel-1, or Sentinel-2, sorry. And then farther down the script, we do the same thing with dynamic world. So a lot of this is just me to expedite the process and make it clear from a description standpoint, just making a copy of the code and changing a little bit of the variables. But you could see that you could put this into some type of loop if you wanted to look at 10 or 100 different time intervals. You could organize your structure or structure your code a little bit different to look at a very large series of pairs, like maybe the spring conditions over a 10-year period might be 10 different intervals like this. All right, a lot of this is in the same code, but then I'll get back down to, there we go, the new code for this script, and that is change detection using the probability bands. We're going to select a particular class to work with. In this case, it's the built class. Could have selected any of the others that we thought might have change. And we want to identify areas that were below a certain probability threshold, and I chose 0.3 for this example. And then the probability of that class at time 2, we want it to increase to over 0.5. And you could structure this in different ways. I'm just saying, hey, look at stuff that was low and now is high with those values. But you could also have a filter that is saying, I don't care what it started with as long as it increased like 0.2 or 0.3 for a probability. So there's all kinds of different ways to structure that, and you could combine multiple probability bands or dynamic world classes into your change detection. But this one is just pretty simple, being the built class. All right, the key line for detecting the change, and I called it new urban because we're looking at the built class, but I guess I could have generalized that to any other class. The probability at time 1 is less than that probability threshold at time 1 that I define, and then the class probability at time 2 is greater than the probability threshold that was defined up ahead. And then in order to visualize change, we're going to have a value of 0 is no change, 1 will be the change, and that will vary from with white and red. So it's a binary variable, new urban, and we define a visualization parameters that are appropriate for that. And then finally, when I am displaying it, I am going to call this update mask on the same variable itself because it's this binary variable of 0 and 1. So that what that means is the only thing that is going to appear in that layer on the screen is when it's a value of 1 because the 0 values get masked out. So that means it's not going to hide everything else. It's just going to highlight exactly where there is areas of change. So let me run that. And I need to go back to figure out where it goes in here. Yep, okay. So this is about where we're at here. If you've walked along the creek, we're kind of in this area over here. But there was identified some significant change in that time period. You could start looking at, what did the Sentinel-2 imagery look like at that time? And I really actually don't know what it is. So, and I'm not sure at this resolution whether it's going to be easy to pick out that either. I have to turn off the area that was built in order to see that. It's a little bit dark there. And it looks like there is some cloud artifacts too as well. So I actually don't know what was built there or why it detected there. But this is kind of a starting point of how you can start looking for or defining areas of change with those class probabilities. We look at the underlying imagery itself to see if we get any clue. I'll turn back on the new built area. I don't know, any Googler that works around here actually knows what's going on in that area? It's at the end of Charleston. Yeah, it could be. Oops, sorry. Yeah. Oh, actually, I know one thing that's out there is there was an area where they had landscaping that they were staging all the trees for a while in these really large pots. I think some of them you could still see down farther here along the path. That might have been the change that happened there. I'm not really sure. Is that right? All right. What else we have going on here? I'm actually going to zoom more over to where I'm familiar with. All right. Oh, hey, this is an interesting one. This is how I get to work each day. So this new built structure that it identified right there is this wonderful bike path that they constructed about 6 months ago. 6 months ago, maybe a year ago, that goes over the 101. So this used to be just marshland, which is still kind of overlooking the marshland, but it has this kind of urban built structure now in the middle of it, which Dynamic World could identify. All right. Any questions on that? It's just, change detection, but the tweak is using a probability band in order to look at the change.
So I think you had set the start date and end date for just 2 years apart or something like that. Is it easy enough to just change that back 10 years or something and run it and then just see big changes?
You could do that. Sentinel-2.
Oh, or whatever. Since
I think I can go back 10 years, yeah.
Yeah, 20.
Let's go 2016
Yeah.
or something like that. And then just for fun, we're going to go to a more dry time of year, though it's been dry for the last 10 years here, so I don't know if that's actually really needed. And then quarter year. See what we get. Yep, we just have the new built that is there. All right, I mean, there's stuff that's showing up here. Once again, I have to get in my neighborhood to figure out, oh, there's some big stuff that's going on the campus. Yeah, over here, I think that's us. Yeah. Yeah, that's us. Well, actually, I guess we're in, no, we are in that one. Yeah, right there. This is the other big building that they're building on the Google campus, which it's been going on for like 5 years, I think, at this point, construction. But. All right, any other questions? If not, let's take a 15-minute break. I believe it's 15 minutes before our next second half section where we're going to start more going in details of how that dynamic world can be used as an input to a classifier.